All right, now let's do some good math. When you have equilibrium math problems, when you have equilibrium calculations, it turns out there are two main types of these equilibrium calculations. Recall that the equilibrium constant is the concentration of products divided by concentration of reactants with a little stoichiometry thrown in there. The two types of equilibrium calculations are given the concentration of products and reactants at equilibrium, calculate the equilibrium constant. The first time is the equilibrium constant is not known. You get these numbers, you measure these concentrations, and you calculate the equilibrium constant. The other type of calculation is when you don't know the concentrations, but you do know the equilibrium constant. Given the equilibrium constant, calculate these concentrations. We will start out by calculating the equilibrium constant when you're given this data. However, almost all of the rest of the semester, when we're done with this, is going to be the opposite, calculating these concentrations when given the equilibrium constant. The next type of reaction we learn is going to be much more common. But let's get this one out of the way first. Okay. Calculating the equilibrium constant given concentration data. Here's an example. You have H2 gas plus I2 gas in equilibrium with 2HI gas. You find that at equilibrium, the concentration of H2 is 0.11 molar, concentration of I2 is also 0.11 molar, and the concentration of HI is 0.78 molar. This is at equilibrium. What is the value of K? All right, the value of K is, first thing, write the equilibrium constant expression. I strongly recommend writing the expression out. Don't put in the numbers yet. Our equilibrium constant expression, K equals concentration of HI to the second power divided by the concentration of H2 times concentration of I2. It's just taking this reaction and writing the expression. Now, once you have the expression written, start putting in your numbers. All right, well, what's the concentration of HI? It is 0.78. But don't forget, we got to put that squared in there. Then you divide that by 0.11 times 0.11. Our concentration is H2 and I2. And we get our answer. It's 5.0 times 10 to the first, or roughly 50. Yeah, not too bad math there. Why I strongly recommend writing out this expression first is because the people who don't write out this expression very commonly forget to square this number. People just want to rush through and say, oh, what's a K? Oh, it's just products over reactants, and they'll take 0.78 divided by 0.11 divided by 0.11, forget to square it, get the wrong answer, and have a bad day. So write out the expression, don't forget to square it. All right. Let's do a slightly more difficult math here. Let's look at this example. Here you have A gas in equilibrium with 2B gas. You find that at equilibrium, the concentration of A is 0.75 molar. But we weren't given the concentration of B. But we were told at the beginning of the reaction, concentration of A is 1 molar. What's the value of K? So here we have an issue because if we work on the equilibrium constant expression, we need to calculate K. We know that is the concentration of B squared divided by the concentration of A from the reaction, but we don't know the concentration of B. We weren't given that. However, we were given enough data to figure it out using what we call an ICE table. And get to love ICE tables. You really have two choices at this point. When you hear the phrase ICE table, you can say, all right, this is awesome, I can do my calculations. Or you can hear ICE table and shrink, shaking, cowering in a corner because you're so dang afraid of them. Choice is yours. Get to love, learn to love ICE tables, and the rest of the semester is going to be much better for you. All right. ICE table stands for initial change equilibrium. And so here's what you write. You write the concentration of A, the concentration of B. You write initial change equilibrium. I am just, in the future, going to write ICE. And you just put in some numbers. Okay, what's our initial concentration of A? It's 1.00 molar. At our initial concentration of B, well, we said at the beginning of the reaction, the concentration of A is 1 molar. We know if it's the beginning of the reaction, there's no B in there. So our concentration of B is 0 at the beginning of the reaction, unless told otherwise. What's going to be the change? Well, We look at our data. At the beginning of the reaction, we start with 1 molar A. It has now dropped to 0.75 molar. So the change was minus 0.25 molar. From there, we can figure out what the change in B is going to be, because if A drops by 0.25 molar, but every A turns into 2 B's, B is going to increase by 2 times that 0.25 molar. So the change in B is just our change in A, minus 0.25, but it's going to be plus 0.25, multiplied by the stoichiometry of our reaction here. If 0.25 molar A goes away, 0.5 molar B comes into existence. Equilibrium is just taking this plus this. What is minus 1, or excuse me, what is 1 plus negative 0.25? That is 0.75. What is 0 plus 0.5? That is 0.5. So now, through this ice table, we know at equilibrium we have 0.75 molar A. Well, heck, we were told that. And we have 0.5 molar B. Through this ice table, we were allowed to calculate the concentration of B. So now we can plug these two into our equilibrium concentration expression. Concentration of B is 0.5 molar, square it, divided by 0.25, divided by 0.75 molar, our concentration of B, and we do our math, and we get 0.33 as our equilibrium constant. All right. Not too bad. Okay, let's run through an example of this. Here we go. Here's our reaction. 2CH4 gas, 2 methanes are in equilibrium with C2H2 gas plus 3H2 gas. All right. We start with 0.15 or 115 molar CH4, no products. So we don't have any products. We start with 0.115 molar CH4. Question, at equilibrium, you find you have 0.35 molar C2H2. That's acetylene, by the way. Question, what is the value for K? What is the equilibrium constant? Well, ice table, easiest way to go here. Because we realize that we're going to need to write down our equilibrium constant expression here, and we're going to have to put in our concentrations to get K. We weren't given all of the concentrations. We were only given the concentration of one thing, or CH4. Therefore, we're going to use an ice table to get the other concentrations to plug in here. So here's our ice table, our CH4, our C2H2, our H2, ICE. I like to draw a line. And okay, so what do we have? Well, we know our concentration of CH4 is 0.115 molar. We know that we have no products. Our initial concentration of these two is 0. We know at equilibrium we have 0.35 molar C2H2, which tells us our change in C2H2 was plus 0.035. Because 0 plus 0.035 equals 0.035. There's some easy math for you right there. Okay, now that we have that, what do we do? Well, let's see. We look at our stoichiometry. Note that if we added 0.35 molar here, our stoichiometry says we're going to add 3 times that amount of H2. So the amount of H2 is going to be 3 times 0.035. And note we also see that our concentration of CH4, note it is going to go away. So it's going to be minus our 0.035. However, stoichiometry says we have 2 there. Okay. So, well, now how do we get our equilibrium constant expressions? Just a matter of math now. This is negative 0.035. That's negative 0.07. So this gives us 0.045. This math here gives us 0.105. Okay, now that we have those numbers, we plug them into our equilibrium constant expression, making sure we don't forget about our 3's and our 2's here. K equals our concentration of acetylene, 0.035, times our concentration of H2, 0.105 cubed, divided by 0.045 squared. All right. The number one mistake people make is forgetting the cubed and the squared. All right. Little bit of math, and we've got K equals 0.020. All right. No problems there. Well, let's crank it up a little bit, shall we? Along with K, there's a very similar deal called the reaction quotient. And the reaction quotient is very similar to K in that our reaction quotient Q for our general reaction here, A moles of A, B moles of B, blah, blah, blah. Q, our reaction quotient equals concentration of C to little c power times concentration D to little d power divided by the concentration of A to little a power times the concentration of B to the little b power. And if you've been paying attention, you realized, wait a minute, I've seen this somewhere before. Isn't that the same thing as K for the general reaction? Isn't K the same thing as this Q right here? And the answer is kinda. The deal is when you're calculating K is an equilibrium constant. By definition, you have to be at equilibrium. When you're calculating Q, you are just putting in the concentrations of your reactants and products, and you do not know if you're at equilibrium or not. We're actually going to use Q to tell us if we're at equilibrium or not, and whether the reactions can go one way or the other, left or right, from that point. Now, at equilibrium, Q equals K. They're the same expression. If you plug in the concentrations and you work it out and find your Q value equals the K value you're expecting, then you're at equilibrium. But what if Q does not equal K? What if you do your calculations and you find Q is less than K? In that situation, if Q is less than K, that means our concentrations are off from equilibrium, and since Q is smaller than K, that means the concentration of C and D are smaller than they should be. And since they're the products, it means to reach equilibrium, this reaction must move towards the right from where it is at to get more C and D to make the numerator bigger to make Q larger. If by chance you find that Q is greater than K, and note that usually only happens if you throw in some product too, you find that Q is greater than K, then there's too much product. And so the reaction needs to shift to the left from this point to get rid of that extra C and D, to get those concentrations smaller, to get the denominator a bit larger. All right. And the most important thing about Q here, Q being larger than K, Q being smaller than K, it tells you where the reaction must go from the point it is at. Q does not tell you if the reaction lies to the left or to the right. The equilibrium constant tells us that the reaction lies to the left or to the right. Q just says, okay, from the point we are at, which direction must the reaction go to get to our equilibrium conditions? All right, we will stop this video here and go through an example to figure out what's going on here.